Welcome to the Explainer. Today, we're going to roll up our sleeves and go under the hood to build a Retrieval-Augmented Generation, or RAG, system. We're going to see how you go from just a folder of documents to an AI that doesn't just guess, but gives you real, verifiable, fact-based answers.
So let's start with a problem that I'm sure you've bumped into. Large language models, or LLMs, are absolutely incredible, but they have a tendency to just make stuff up. They can generate answers that sound totally plausible, but are actually, well, wrong. It's this thing we call hallucination.
Now, why does this happen? It's because an LLM's knowledge is basically frozen in time. It only knows what it was taught during its training, and that data could be months, maybe even years old. And, just as important, it has no way of accessing your private or super recent documents, like, say, your company's internal files or the latest research papers.
So how do we fix this? Well, that's exactly where RAG comes in. We're going to walk through what it is, how to build its two main pipelines, and really understand why it's such a game changer for making AI something we can actually rely on.
Okay, so what in the world is RAG? Honestly, the best way to wrap your head around it is to think of it like giving an AI an open book exam.
Think about it. Instead of forcing the AI to answer from its old, static memory, RAG gives it a hand-picked library of documents it can reference. So before it even tries to answer your question, it first looks up the relevant facts from sources that we provide and trust. This one little step makes sure the final answer is grounded in actual facts, not just some half-remembered training data.
Now this diagram shows you the whole RAG pipeline, start to finish. I know it might look a little complex at first, but you can really break it down into two main stages. First, there's the ingestion phase. That's all the prep work we do ahead of time to build our knowledge library. Then, second, you have the retrieval and generation phase, which is what happens in real time whenever a user asks a question. Let's tackle that first part, ingestion.
All right, let's get into part one, building the knowledge library. This is the super important offline step where we get all of our documents and information ready and make it easily searchable for the AI. We call this whole process the ingestion pipeline.
It all breaks down into 4 key steps. We're going to load our documents, chop them up into smaller pieces, or chunks, then create these numerical representations called embeddings, and finally, we'll store everything in a special kind of database.
So first things first, we load up our source documents. And this can be pretty much anything you can think of. PDFs of research papers, internal company wikis, technical manuals, you name it. The system just gobbles up all this raw information.
Okay, now we get to what a lot of experts say is maybe the single most critical step in this whole process, chunking. And it's a simple idea, really. It just means breaking down those big, long documents into smaller, more manageable, bite-sized pieces.
So why is this so incredibly important? Well, LLMs have a limited attention span, what we call a context window or a token limit. You can't just feed an entire textbook into the prompt and expect it to work. By breaking the text up into these small, focused chunks, we make sure the AI gets only the most relevant information, and that dramatically improves the accuracy of its answers.
So, is there a magic number for chunk size? Well, kinda. Sources suggest that the sweet spot for top performance is somewhere between 300 and 500 tokens per chunk. It's also a really good idea to add a little bit of overlap between the chunks, say 50 or 100 tokens. That just helps make sure you don't accidentally chop a key sentence or a critical idea right in half. Okay, so we've got our neat little chunks of text. Now we need to translate them into a language that machines can actually understand. And this process is called creating embeddings. An embedding model basically turns each chunk of text into a long list of numbers, what we call a vector. And this is the real secret sauce. Because now the computer can use pure math to figure out how close 2 pieces of text are in meaning. A chunk about electric cars will have a vector that's mathematically very close to a chunk about automobiles. It gets the relationship. And finally, we need a place to put all of these vectors. So we use a special kind of database called a vector database. A tool like FAISS, for example, is incredibly fast and good at one thing: finding the vectors in our library that are most similar to a user's question. And just like that, our knowledge library is built and ready for action. So with our knowledge library all indexed and good to go, we can finally move on to part 2, answering the question. This is the real-time pipeline that kicks into gear the very moment a user types something in.
This pipeline also has a few key steps. We take the user's query, use it to retrieve the most relevant context from our library, beef up the prompt with that context, and then finally generate the answer.
The whole thing starts the instant a user asks a question.
First, we take that question and we turn it into an embedding, using the exact same model we used on our documents. Then, the system does a super fast similarity search in our vector database to find the text chunks whose vectors are mathematically closest to the question's vector.
And this is where the magic really is. This is the power of what we call semantic search. It's not just looking for keywords. It's finding chunks that are conceptually related, that match the meaning and the intent behind the question, even if the exact words are totally different.
Okay, so how many of these chunks should we actually pull from the database? This is what's known as retrieving the top K most similar chunks. And as you can see from this research data, there's definitely a sweet spot. Retrieving about 5 chunks often gives the best results. If you grab too few, you might miss key context, but if you grab too many, you can actually confuse the LLM with a bunch of irrelevant noise.
This step right here is the augmented part of Retrieval-Augmented Generation. The system takes those top 5 chunks it just found and basically staples them to the user's original question. This creates a brand new, super information-rich prompt that we're about to send over to the LLM.
So the final prompt that the LLM actually sees looks something like this. It now has the user's question, and it has all the relevant factual information from our documents right there in front of it. We've literally given it the open book.
Okay, let's pull all this together. Why does any of this matter? By building this RAG system, we've basically transformed a standard LLM from this kind of black box that relies on old memories into a transparent, trustworthy tool that grounds all of its answers in facts that we can actually check.
Because we're grounding its answers in specific, verifiable sources, RAG pretty much eliminates hallucinations. It lets an AI use up-to-the-minute or even private data safely and effectively. This just blows the doors open for AI in countless professional fields. And it leaves us with one final, really important question to think about. As these systems get more and more powerful and accurate, what are the new challenges we're going to face in governing them?